Hello. Purpose of today's lesson is to explore complex numbers, how they're represented graphically, and how that enables us to write complex numbers in two different forms, Cartesian form and polar form, as indicated by the instructions up here. The benefit to Cartesian form is clearly known because that's the same as how we plot vectors. That is, we go over and up. It's the same way we plot points. It's how we plot vectors. So we understand Cartesian form based off of our classical training in mathematics. Polar form, on the other hand, deals with the direction of the vector, or the complex number in this case, and the magnitude. So there's two different ways of looking at the same number, the same complex number. The benefits for actually writing in polar form are going to become clear as we proceed, but you'll find that working with complex numbers in polar form is so much easier than working with numbers in Cartesian form. And so that's what we're going to explore later on in this chapter. But for today, we're just going to hammer out the basics and how to express from one form to another. I would like to establish right away that we should be making connections to what we learned when we did right triangle trigonometry, and we should also make connections to what we learned when we studied vectors, and realize that everything that we're doing here, everything that we're talking about, is completely consistent with the language and philosophy of those two other subject areas. The benefit for you then is this shouldn't require any new learning. This is simply applying old learning to a slightly new context. So let's proceed. The issue here is we want to convert 2 minus 3i into polar form, and so basically this is Cartesian form, and we want to be able to see it in polar form, and we'll see what that looks like in just a moment. Now, the first thing that I'm going to do, and this is something that everybody should do, is immediately make a picture. We need to make sure that we know what quadrant we're in, and we also need to make sure that we understand what kinds of numbers we should be looking for. So if we accurately plot the 2 minus 3i, plot it accurately as a vector, then the numbers and results that we get when we do our work should be consistent with what we see in the picture. So I make the picture, so I anticipate outcomes. Here, for example, I'm looking for theta. I can guarantee you that theta is going to be a negative number, because when I take the arctangent of a negative ratio, I'm going to get the negative angle associated with it, because that's the definition of arctangent. It's only for positive or negative pi over 2. So the magnitude as well, given that this is a three-sided and two-sided, we should anticipate our magnitude being somewhere, in the reasonable, somewhere around larger than 3, but not by much. We can find it by using Pythagorean theorem, just like always, and we get the square root of 13. Once again, the square root of 13 we know is going to be smaller than 4. It's reasonable, and it's also bigger than 3. And it's reasonable that this hypotenuse is smaller than 4 and bigger than 3. So once again, the picture has some benefit to us in making sure that we got everything working out the way it's supposed to. Additionally, I should know that I am in radian mode and not degree mode in my calculator, because the negative 0.983 is consistent with almost 1 full radian rotation. This looks like it's just around a 60-degree angle or so. 57 degrees is 1 full radian. It looks like that's how far we went. So I'm saying all this to remind you that we should not just focus on the procedures, but understanding the nature of the procedures and making sure that we're supporting visually what we're doing symbolically. Anyway, I'll get on with it. The shorthand for polar notation is going to come up in just a moment, but essentially what we have is two sides of a triangle, where if we took the cosine of the angle, we would get the horizontal piece or leg of that triangle, and we need to scale it up, square root of 13 times bigger, to account for the fact that the hypotenuse is not 1 like it is on the unit circle. So I have the original cosine length scaled up to a square root of 13 factor, and then the vertical part is multiplied in the imaginary number line, so it's I times the sine of that angle, and once again that should be consistent with what we see in the picture. Oh, I'm sorry. What I meant to say was that number, the sine of the angle we're dealing with here, is a scaled down version. We need to scale it back up to square root of 13. Sorry, I lost my way for a little bit there. I was distracted. So anyway, this is a clunky form for a complex number. But we can use the shorthand by recognizing C for cosine, I for the imaginary part, S for sine, abbreviated as CIS. and then we put the angle in there and the magnitude here, and this is our shorthand form of the vector z. So this is z in Cartesian form, and this is z in polar form with shorthand. So going back and looking at examining the figure that's given to us here and understanding Cartesian form we know. Polar form now is simply a reckoning of the r representing the length of the radius. And I should actually amend this. This is supposed to be magnitude of r times cosine of theta plus I sine theta. So I'm trying to do something here. It's not working. Some lag. Okay, done. Anyway, the magnitude of r, once again, I'll put my little magnitude marks. It looks like I need to calibrate this stylus. Anyway, the magnitude of r is calculated with Pythagorean theorem, and the angle theta is just using inverse tangent. So, moving on. What if the situation that I was dealing with was just like we saw before with 2 plus 3 or minus 3i? What if I changed it oh so slightly to this Cartesian form? Graphically, I could see that now all of a sudden I'm in the third quadrant. The work that I do is going to be consistent. I find the magnitude, and the magnitude of 2 minus 3i is square root of 13. So it shouldn't be no surprise that this vector is as long as the vector we saw previously. The angle, however, you'll notice I use phi instead of theta because I'm going to still find the arctangent of negative 3/2. But we should know that when we take the arctangent of negative 3/2, we get a fourth quadrant angle. So we have to visualize that the calculator is going to give us this angle over here when we want this one over here. We should also understand that that is going to be exactly pi radians away because the two vectors form a line. So all we have to do is to take this value, this angle, add pi to it, and that will be the angle theta that we're looking for. So I get approximately 2.16, that's rounded, and then we can go straight to the shorthand magnitude of r times the cosine plus I sine of theta. So that's the only difference. We have to make sure that we understand what our inverse, our arctangent, and arccosine and arcsine are going to give us, and make sure that's consistent with the quadrant that our Cartesian form is putting us in. Just quickly now, to reverse the process, if we know information about the magnitude and direction, either expressed in this form, that is, the magnitude of z is this, and the argument of z, argument is the word for the angle. If I know this information, then I have enough information not only to plot a picture or a graph of that complex number, but it's also enough information to convert back into Cartesian form. So I draw an angle that looks like 60 degrees. I indicate the magnitude of the vector to be 4 units long, and then I identify the following. It says here, if I follow the diagram, that if I take magnitude times the sine, that gives me the vertical piece, and if I take the magnitude times the cosine, that's going to give me the horizontal piece. Now we could try to memorize that, and hopefully we'll be successful someday, but it's more important, in my opinion, to just remember that if this were a unit radius, that is 1 unit instead of 4 units, we define the unit radius to have a cosine of the angle to represent the horizontal side, and the sine of the angle to represent the vertical side. Since this radius is 4 times longer than the unit radius, then both my legs, because they're similar, are going to be 4 times longer than the unit sines and cosines. So it's really a simple adjustment from what we learned in trigonometry to understand how we work in the complex number plane. By the way, I should be specific here that when we're doing this, we're graphing real numbers against imaginary numbers. So we have the real number line and the imaginary number line. And that causes an argand plane. Anyway, to find the Cartesian plane, all we have to do is translate from polar form. Now this aside right here is recognizing that, first of all, in polar form, we can factor out the common factor of 4 and just bring that in front as the magnitude of the radius. And then I can impose my shorthand. So this is the original polar form that we would expect to see on an IB exam. 4 cis pi over 3, or 4 parentheses cosine pi over 3 plus I sine pi over 3. Either of these forms is how we start in polar form. Nonetheless, I distribute the 4 here because each component is going to be 4 times bigger than the unit component, and all I have to do, after I wait for my writing here, hold on, all I have to do now is evaluate the cosine of pi over 3, which is a half, and we should know that by now. Sine of pi over 3 is square root of 3 over 2, and simplifying, I get this z-value. It's important, again, to think about our results and make sure they make sense contextually. For example, we might be the student who says the cosine of pi over 3 mistakenly is square root of 3 over 2. We might accidentally say the sine of pi over 3 is 1/2. If we were to do that, come here and look at the picture is not consistent with those results. Rather, when I say the horizontal is half of the length of the hypotenuse, that's consistent with everything I know about 60-degree right triangles. This 3.46 being about 86% of 4 is also consistent with what I know. So these results are definitely spot on. I even checked without a calculator here just to show that 4 squared plus, or 2 squared plus 2 squared or 3 squared equals 4 squared or 16. So I checked everything. So hopefully this is helpful. Sorry I went on for a little bit, but maybe hopefully you watched it in small doses or something. But have a great day.